Okay, the first thing we want to look at in this problem is we want to find out what the linear model that describes demand as a function of price. And we're going to use the data in this table here in order to do that. Take note, by the way, that the cost of producing X units is actually, this should be C is equal to 200X plus 100,000. So in other words, for each unit it costs us $200, and plus there's a startup cost of $100,000. Okay, so if we look at this linear model, we can see that every time we go up by $100, the price goes down by, or the total revenues, or demand rather, goes down by 2,200 minus 1,750, and that gives us a total of 450. And that's consistent with what we see elsewhere. When we went down, or we went up from 200 to 400, we went down from 3,100 to 2,200. So that gave us a difference of 900, and that's going to be divided by 200. So in both cases, we end up with a demand is equal to negative 4.5 times the price, and then we have to then add our value of, so let's see here, when we multiply 200 by negative 4.5, we get negative 900, so we have to add 4,000. Okay, so now we have our demand curve, and what it shows us is that as the price increases, the number of pairs of boots that will be demanded goes down, which of course makes sense. Okay, so let's go on to our next question here. Okay, so what is the model that expresses total revenue as a function of price? So we now have that our demand is equal to negative 4.5p plus 4,000. And what we know is that every time we sell a pair of boots, we're going to be selling them for a price that's equal to p. And so that means the total revenues that we generate will be equal to the number of pairs of boots we sell, which we said was given by this expression, multiplied by the price per pair of boots. So we end up with a quadratic of negative 4.5 p squared plus 4,000 p. That is our revenue equation now. So revenue is equal to negative 4.5 p squared plus 4,000 p. Recall, we have that cost was given by the equation 200d plus 100,000. So we have, okay, so then we go on to our next question, and here we have a question, what is the model that expresses total cost as a function of p, the price set by the manufacturer? Well, as you recall, 200d plus 100,000 is our cost, equals 200d plus 100,000 as our cost. Okay, what we want to do is we want to express this C now as a function not of D but of P. And since we know that D is equal to negative 4.5 P plus 4,000, we can replace D with that, and that gives us C is equal to 200 times negative 4.5 plus 4,000 plus 100,000. So when we work that through, we get, negative 4.5p, we get C is equal to, when we multiply this, we're going to get negative 900p plus 200 times 4,000 is going to give us an 8, followed by 1, 2, 3, 4, 5 zeros, or 800,000, plus another 100,000. So our total cost then is equal to negative 900p plus 900,000. Okay, so now we have to figure out the expression that gives us our total profits. Well, we know that it's going to end up being as a general rule, are our revenues, the amount that we earn from selling the boots, minus C, which are our costs from selling the boots. So as we see, our cost is equal to negative 900p plus 900,000. Our demand, we said, or rather our revenues, was equal to negative 4.5 p squared plus 4,000 p. Okay. So what do we end up with? All right, when we work this through, we end up with negative 4.5 p squared plus 4,000 plus 900, so that's going to give us plus 4,900p minus 900,000. Okay, that is our profit function. Okay, so what do we do from here? Well, we want to figure out how do we maximize our profits. And so, because we have a quadratic, that means that we are going to figure out what is the vertex of our quadratic. And so in order to do that, we have the form currently is the standard form. So we're going to find the x value of the vertex, which will be the price that we're going to set. So we're going to use that the x value of the vertex is equal to negative b over 2a, which means that it is equal to negative 4,900 over 2 times negative 4.5, which means we're going to end up with negative, let's cancel out this negative, so we end up with 4,900 over 9. And when we divide that through, we end up with 544.44 as the price that we will set for each pair of boots. When we then plug that value into the equation, we end up with this value, 433,888.89. And so that, in dollars, is our expected profit per week, according to the original setup of the problem. So we'll set the price at $544, and we might round it because we want to have something that's not so off-putting as a price. And our profit that we anticipate is $433,888.89. Okay. So then we're asked what is the minimum price that the company should set and still make a profit? In other words, at what point will this thing, so let's say if we sketched it like this, what is this price point right here? Because that's the point at which they will set the lowest possible price and they'll break even, so anything beyond that would yield a profit for them. So now what we need to do is figure out, well, where in fact does this thing cross the x-axis? So again, we go back to our original equation for profit, which we said was negative 4.5 p squared plus 4,900, excuse me for that, 4,900p minus 900,000. Okay, and so then we're going to plug that into our quadratic formula, which is going to give us 4,900, negative 4,900, plus or minus the square root of 4,900 squared minus 4 times A times our value for C, 900,000. All of that is over 2A or over -9. Okay, so that's the kind of calculation we like to ask our calculators to do. And when we do that, we end up getting two values. We get $233.93, and we end up with $854.96. So this price right here represents the lowest point at which we can still break even, and this would represent the highest price we could set. So at this price, we're selling a lot, but we are not making much profit from each, and but we'll still at least break even. And as you recall, the cost function was that it costs $200 to make each pair of boots plus a set amount of money. So we're only selling the boots for $233.93. So we're not going to be able to make much profit if each pair of boots costs us $200 to make. Okay, let's take a look at this next question here, which is that Wellington is willing to sacrifice some profit by reducing the price in order to gain market share. They decide they're willing to accept a minimum profit of $250,000 per week. What price should they set for their boots, and what will be the number of pairs they sell per week? So basically what we're asking is, again, if we think about our function looking like this, we're saying if we want to be somewhere above here, where this line is equal to y is equal to $250,000, then what's the x value right there and right there, and and how many pairs of boots does that represent? So if we think about our profit function, which we had as -4.5 p squared plus 4,900 p minus 900,000. Well, now instead of setting that equal to 0, we're going to set that equal to 250,000. And when we do that, we then want to rework it so that we again have another quadratic, which is set equal to 0. And we're going to subtract 250,000 from both sides, which will give us 1,150,000 negative on this side, and that is going to be equal to 0. And then we want to find the roots of that. And so in order to do that, we again go to our quadratic formula, and when we do that, we come up with the following values. So our two x values that we come up with here are 342.3, which is this x value here, and 746.59, which is this x value right here. So we're going to choose the lower of these, the lower price point, and when at $342.30, and when we do that, the number of boots that we're going to sell, we can calculate by plugging into our demand equation. So we'll have -4.5 times 342.3 plus 4,000, and that's going to give us a number of boots that we sell of 2,459.67, or around 2,460 pairs of boots. And so what we're saying is that when we set our price at around $342.30, we will sell around 2,460 pairs of boots, and we'll make a profit, which is the minimum that we set for ourselves, of $250,000.